Okay, this is a video presentation from Case Study 2 in the course Icons 189 from Team 12. Our topic is what matters in building a fusion reactor, and our team members are Amira Garba, Skylar Lamb, and E. Ding. We will begin with some background information from myself and E. So what is fusion energy? Fusion energy is a type of nuclear energy opposite from fission, where in a thermonuclear process, atoms are heated and forced together, creating new atoms, and leftover mass is turned into energy. That energy from the reaction is collected into electricity. The reason why we decided to research this topic is because fusion energy could have a huge impact in reducing climate change. So, fusion energy and climate change. Fusion energy, unlike fission or fossil fuel energy, does not create any waste and it is clean, renewable energy source. The fuel used is also abundant deuterium, which is found in the ocean.
So does fusion energy safe? And some people believe that fusion reactors are dangerous and risky to the safety of people if that's up and running, but in fact, it's a lot safer. Unlike fission reactor failures, if there's a failure in fusion power plant, the plasma will just expand and cool quickly. Fusion also doesn't create toxic waste, meaning there isn't a problem of nuclear radiation contamination wildlife if there is a breach. And why does people are studying fusion energies right now? Before we didn't know if fusion was possible at all. It's a brand new source of energy. Experts are trying to master, therefore, there's not a lot of information about current fusion reactors. However, as recently as this April, Tay Technology successfully produced a fusion reactor that was commercially viable, sparkling interest in energy companies rather than only the scientific ones. So, what are some setbacks for people studying fusion energies? The first one would be the cost. Developing nuclear fission is incredibly expensive, with much of the flashback being the cost of making a reactor to begin with. The second is that up until recently, we didn't even know if it actually worked, and there's still a debate as to if it worth the cost or if it's as revolutionary as we think. And the third setback is that if the goal to gain energy without increasing carbon emissions, solar, wind, hydro have already proven themselves as reliable green energy sources. With this knowledge, I will pass the presentation to Skylar, who will discuss the study design and what we are trying to do.
Okay, thank you. Before getting into our experiment, a large caveat is our lack of data. Because this topic is so new, there really isn't much useful data on fusion reactors that we could find. In our study, we wanted to answer the question, how much does temperature, magnetic field strength, and size matter when improving the containment of plasma in fusion reactors? We chose these three factors because of the way the fusion reactors work. They must maintain a certain temperature, use electromagnetism to maintain pressure on the plasma, and limit the plasma to a certain volume. Our hypothesis is that there's a certain combination of these three factors that will optimize a hypothetical fusion reactor to output more energy than we put in. We then plan on collecting our data from several different reactors, plot energy output as a function to these three factors to determine if there's any correlation, and then make suggestions on possible combinations of traits for a fusion reactor in the future. Now on to the graph with the mirror and what it means.
For our data, we collected information on three different fusion reactors located across the globe known as Jet, Iter, and East, plotted their temperature, magnetic field strength, and size compared to their energy output. As you can see on the graph, the larger minor radius, which is the radius of the path that the plasma current flows, and a stronger magnetic field strength causes a bigger energy output. Magnetic field controls the flow of plasma, which again is what we absorb the energy from. Plasma is the state of matter that deuterium will need to be in after applying very high temperatures. In conclusion, as we stated before, we don't have enough information. So far, with the tier being the most successful, the most we can say is to imitate their reactor.
The photo that you see on the poster is of the jet fusion reactor, and it shows what exactly the plasma container looks like. So when we talk about the minor radius, it's like the column that you see in the middle, and the major radius is obviously on the outside, and technically where the camera is sitting is where the plasma would be.
And that's it for our presentation. Thank you so much for watching.
Thank you.
Thanks.